Hey everyone, I just wanted to do a little recap of the 6.1 and 2, which is solving systems of linear equations. So 6.1, there's no lesson on it, but I want us to be familiar with some vocabulary. So basically, we have three different types of solutions to a system. We have something, and you should be familiar with like this vocab, where you have no solution, one solution, or infinite solutions. In general, if there's no solution, we call it an inconsistent system. Versus if there is a solution, we call it consistent. Then if there's only one solution, think about the two lines. They're independent, they're separate. And if there's one solution, right, you can think about them being like the same line, so they're dependent on each other. But that will be some vocab that you hear throughout this unit, so just be familiar with it. But there's nothing you actually have to do. Just be aware we kind of have that background of 2x2 systems, but we're going to focus today on a 3x3 system. So a 3x3 system is actually like planes. So as you can see, like a picture, there's three planes that intersect and there's infinite solutions. Then it forms a line. And then if it's helpful to think about, this is what they call a consistent system because there's a solution, but since there is like that whole line, that line depends, or the answers are dependent on each other. One solution is also a consistent solution, but they are independent. You know, see that as like three separate planes where there's only one point where they cross, versus no solutions means that it's inconsistent. And notice just like the lines, we have parallel planes here. Okay, I wanted to warm us up, and I'm like, hey, if I give you a 3x3 system and one of the letters is already solved, so if we look at this first one, you already have z equals 5. I recommend with something like this that you use substitution. If you already have one of the letters, plug that into z. And then let's look at, why did I choose this one? Because notice this one only has y and z, so then I can figure out why. If you plug into the bottom one, you see where you have x, y, and z? I wouldn't be able to figure out x and y at the same time, so let's just start with finding out this one right here with the y's. So we'd have y plus 1/3 times 5 equals 20/3. So y plus 5/3 equals 20/3 minus 5/3 on both sides. So y equals 20 minus 5 is 15/3, which equals just 5 as well. Okay, and then you've got, in this case, we also want to find z. In this case, since we have both a y and a z, we're going to place both of those variables. So we know it's x plus 1/6 times 5 was what we found for y just previously, plus 1/3, we were given that z is also 5, equals 5/2. So we have x plus 5/6 plus 5/3 equals 5/2. Okay, this is one of those things you can start to pull out your calculator if you want to do some mental math. Think about this. To make it a common denominator of the 6, we're going to multiply by 2 over 2. So we get 5/6 plus 10/6. So we get x plus 15/6 equals 5/2. So we're going to subtract 15/6 from both sides. Once again, if you want to kind of do some mental math, think about this as 3 over 3. So that is equivalent to 15/6 as well. So x equals 0. So you can write your answers like x, y, z separately, or otherwise we usually see it as 0, 5, 5, and we would say that this is a consistent and then dependent system, meaning there's one solution. Okay, in general, when we're solving a 3x3 system of linear equations, I have some steps on this next page, but we usually use elimination to start with. So I would target one of the three variables. For example, like decide that you're going to eliminate like the x's or the y's, right? Eliminate that from like two of the pairs. So maybe the first and the second and the third, or the first of the third. So it's got to be separate pairs to get a new system of equations, which would then be a 2x2 system of equation. You'll have two variables and you're solving that and then kind of backtracking with substitution. So let's go ahead and see what that looks like. So as we focus here, you can either focus on the x's, the y's, or the z's. In this case, I really feel like any of these options could be good because at least there's one of like each of those variables in a column. If you had something that had like 3y, 2y, and then negative 5y, I would not use that column because it's not going to be as easy to have things cancel out. So let's arbitrarily just choose like the x's. So let's focus on trying to cancel out those x's. So I'm going to go ahead and do the first row, which is negative xy plus z equals negative 4. And let's say I choose that first and that third row. So let's say I'm going to use this first one and that third one. I'll show you in a minute why I chose those two. And that's because I just have an x and an x there. So think about timesing that third row by a negative 1. Do you see how then you'd have an x minus x? They cancel each other out. That's the idea of elimination. So then I'd have plus 5y minus 2z equals 18. So let's go ahead and let's add those together. I personally prefer to multiply by the negative and then add, but you are also welcome just to subtract, which is equivalent. So in this case, your x's cancel. We're left with 4y minus z equals 14. And we're going to use that in a minute. Now let's focus maybe on like this top row. And if we want it to cancel with a negative 3x, we're going to multiply that top row by 3. So we have 3x minus 3y plus 3z equals negative 12. Similarly, you could have multiplied the bottom row by 3 and then added to the second one. We just can't use the first and the third again. So I'm just writing that second row. And your x's cancel. We have negative y plus 7z equals negative 17. So I now have a 3x3 system here. Sorry, 2x2 system. These simplify down to 2. So I have 4y minus z equals 14. I've got negative y plus 7z equals negative 17. So we want to think about solving that system. In this case, I'm going to maybe try to get rid of the y's. So let's think for a moment what happens if I multiply this bottom row of y by a 4. So then I'd have negative 4y plus 28z equals negative 68. So now I'm going to add that top and that bottom. I kind of just crossed out that middle one so I didn't get confused by it. So I've got my y's cancel. I've got 27z equals negative 54. As you divide both sides by 27, you get that z equals a negative 2. So now it's a matter of plugging that back in. So maybe I go over here and I'm like, okay, I'm going to plug in that negative 2 for z. So I've got 4y minus a negative 2 equals 14. You really can use either equation. This is just the first one. You can go back to this green one though as well. We're going to want to go to one of those two that just has z and y in it. So now we have 4y plus 2 equals 14. Subtract 2. 4y equals 12. Divide by 4, and y equals 3. Okay. So now let's look at, we've got z, y. So now we're going to go back to one of these three original equations and find x. I'd probably use the top or the bottom one because see how they already have x alone. So let's say we use the top one. We'd have x minus 3 plus a negative 2 equals negative 4. So x minus 5 equals negative 4. Add the 5 to both sides, and x equals 1. So quite often, you're welcome just to kind of circle those three answers, but quite often we will write it as an ordered triple. So 1, 3, negative 2, which is a consistent and then dependent solution, meaning there's, independent solution, meaning that they are separate, right? There's only one point. All right, let's try it again. So once again, as you look at these problems, the first thing you want to decide is you want to decide, okay, are we going to solve for x, y, or z? In this case, once again, if there's like lots of, like there's 1x's, that's a good sign, right? I could like try to solve for the y's because there's a 1y, that's good, that's easy to multiply, or even like the z's. In this case, let's try something different. So let's try solving for like the z, canceling the z's out, especially because you have a z and a negative z. So notice how when you add that first and second row, they're already cancel out. So I'm going to add 3x minus 2y plus z equals negative 5, and I'm going to add x plus 3y minus z equals 12. So I get 4x plus y equals 7. Okay, now I'm going to do the same thing, but I've got to use something else. So I'm going to have to use this third row. I kind of got to ask myself, well, what can I maybe multiply? I can either do the first or the second. Since the second one's already negative and I like them to be opposite signs, I'm going to multiply that second one by a 2, so a negative 2z would cancel out with that. So I have 2x plus 6y minus 2z equals 24, and x plus y plus 2z equals 0. 2x plus x is 3x, 6y plus y is 7y equals 24. Okay, I now have a 2 by 2 system, right? That just has x's and y's. So you can think about it as like the 4x plus y equals 7, and 3x plus 7y equals 24. So notice to have, let's say we have the y's cancel. Ideally, if you have those ones, that makes things easier. You could have the x's canceled, but you're going to multiply one by like a negative 3 and the other one by 4, which is just a little more work. I'm going to multiply this top row by a negative 7. So I have negative 28x minus 7y equals negative 49. Okay, now I'm going to add my two rows. So I get negative 25x, your y's cancel, equals negative 25. Divide both sides by negative 25, x equals 1. Okay, perfect. Now that you have that, choose one of these other two equations that we created that just have x and y to plug it into. So maybe I do 4 times 1 plus y equals 7. So that's 4 plus y equals 7. Subtract the 4, y equals 3. Okay, we're 2/3 of the way there. Now it doesn't matter, we gotta use one of your original ones. Since I'm solving for z, maybe I'll use this top one because it's a little easier because z's all alone already. So I've got 3 times x is 1, minus 2 times 3 plus z equals negative 5. 3 times 1 is 3, minus 6 plus z equals negative 5. 3 minus 6 is a negative 3 plus z equals negative 5. Add 3 to both sides, and z equals negative 2. So once again, you could write that as an ordered triple, but this is a consistent and then independent system. Okay, we've got 2 more to do. Okay, as you look at this top one, the fact that this bottom row is already in terms of x and y, if I can use these other 2 equations and eliminate z, that'd be super helpful because then I already have my 2 equations that have x and y. So it kind of takes out a step for you. So I'm going to think about adding these 2 to eliminate z. So you'd have x plus y plus z equals 4, and 2x minus 4y minus z equals negative 1. So you get 3x minus 3y equals 3. And I'm going to combine that with this equation. So to have your x's cancel, maybe I'll multiply this times a negative 3. So now I have the 3x minus 3y equals 3. That comes right there. And I'm going to use this one for my other one. So negative 3x plus 3y equals a negative 6. As you add this, 3x minus 3x, that gives you 0. And you also have negative 3y plus 3y, that also gives you 0 equals negative 3. So you get 0 equals negative 3. That's not a true statement, so we get no solution, which means the system is inconsistent, meaning there's no answer. Okay, this next one's a little bit different because it only gives you two equations. So it says like x plus y plus z equals negative 10 and y minus 2z equals 0. And notice how it tells you to put x and y in terms of z. Okay, the fact here that there's only two planes, it means that they're going to have to intersect at a line. So if you go back up to like this picture that I showed you before, think about if you only had this plane here, and then you only had this plane here, do you see how they would have to intersect in a line? So that's kind of like the visual representation. But let me show you a little bit algebraically about how that works out. So it says, note, put x and y in terms of z. So first of all, if I solve this one for y, if I add the 7z to both sides, do you see how you have y equals 7z? So this almost reminds me of substitution, like, hey, let's plug that in. Let me do it this way. Let's plug that in for y then. Now I have an equation like x plus 7z plus z equals negative 10. So this is x plus, you add your z's, you get 8z equals negative 10. Subtract 8z from both sides. You say x equals negative 10 minus 8z. So notice how the answers you're getting for x and y are in terms of z. So this is a system that does have infinite solutions, which means it's a consistent and then dependent solution. And even though it says infinite solutions, it does not say any point works. Like if I have, so in the way that these are arranged, think about this as x, y, and then z. They're saying let z be just z. We're going to leave it as is. But when we look at y, it's defined, y is the same as 7z, and x is the same as negative 10 minus 8z. So like if we know that z is 1, that means that y is 7, and when you plug 1 in over here, x would be 18. So there's a specific like ordered pair that works. It's not like 1 on 1 would work. However, for any z you choose, like if you plug in 0, we'd have 7 times 0. Then you'd have negative 10 minus 8 times 0, so you'd have negative 10. Like any of these pairs work. And I just think that's important to know. Okay, one last example, and it's a word problem. Our favorite, right? Okay, it says solve the system in context. In a bag, a child has 195 coins worth $7.80. There are 3 types of coins: pennies, nickels, and dimes. I'm going to use penny, PN, and D for pennies, nickels, and dimes. If the bag contains the same numbers of nickels and dimes, how many of each type of coin are there in the bag? Okay, so let's first of all think about it. Okay, if there's a total of 195 coins, that means if we add our pennies, our nickels, and our dimes, we'll have a total of 195. Same numbers of nickels and dimes. That means whatever N is, it's going to equal D. Actually, I can move that just down a bit smidge. N equals D. Then you've got this amount of money. So this is where you're going to remember that pennies are like 5 cents, nickels are 10 cents, and dimes, just kidding. Oh my goodness, pennies are 1 cent, nickels are 5 cents, dimes are 10 cents. You've got 2 options. You can either do like 0.01 P plus 0.05 N, but I almost think about this a little bit easier, as this is 780 cents, and that for me is easier than dealing with all those decimals. So we've got 1 for penny is 1 cent, plus 5 for the nickels is 5 cents, plus 10 times the dimes is 10 cents, equals 780. Okay, you can solve this however you'd like. Like we could start using elimination. The fact though that I have N equals D, I would go ahead and choose, like let's say we choose N. I'm going to go ahead and replace N with D in both my equations. So I could write this as P plus D equals 195. That's really P plus 2D equals 195. And same thing in this other one. You have P plus 5D plus 10D equals 780. So as you combine your like terms, you really have P plus 15D equals 780. I think it said 580 before, I apologize. So think about changing these signs. If I subtract it, notice how you'll just have your P's cancel there. So I've got negative 13D equals 195 minus 780 is negative 583. Divide both sides by 13. And D equals 185. My apologies. Okay, sorry. This is 185 divided by 13. Let's try that again. We get D is 45. Okay, if D is 45 and we know that N equals D, that means that N has to also be 45. So now you just got to choose what equation you use to solve for P. So maybe we can use that first one. P plus 45 plus 45 equals 195. So P plus 90 equals 195 minus 90. So P equals 105. So in this case, we have 105 pennies. We got 45 nickels. And we got 45 dimes. Hope